Welcome to More to Know, a podcast to explore beyond the headlines. In every episode, we'll take a look at a topic and bring together voices on the subject who are experts or directly involved. We'll talk about what's in the news, science, technology, some sports, and just things that have, well, more to know. I'm your host, Christopher Conover. In this episode, more to know about space and how we see what's out there. Space, the final frontier as it was called in some little TV and movie series, is in the news a lot right now. There's the excitement of the Artemis mission as the U.S. gets closer and closer to returning people to the moon. Then there's the wandering supermassive black hole spotted by astronomers. Also, a planetary system recently discovered in our galaxy that is so, quote, starkly different than our own that scientists are struggling to find terms to describe it. Dr. Erica Hamden is an astronomer, Guggenheim Fellow, and the director of the Space Institute at the University of Arizona. She says for astronomers, making those discoveries is a little different than the work of other scientists.
Astronomy as a science is tricky because, what you're supposed to do with science is have a hypothesis, develop an experiment, test the hypothesis, run the experiment, see what your data says, and then, do the loop continuously as you figure things out. For astronomy, there's no experiment. You can't, build a star in the lab or watch a galaxy rotate. We are looking at these objects that are so far and that change on timelines that are just not available to a human. So a lot of what we have to do is just look at things, look at many of them, and then kind of try to figure out what's happening. And what we're actually looking at is the light that is coming off of these objects. Sometimes the light is made by them, sometimes it's reflected light. And ultimately, we're just looking at photons. What is nice is that at least there are many characteristics of the photons. So how much light is there is one thing, but also what type of light. Is it the higher energy, lower energy, what wavelength tells you a little bit about what the process is that's happening? Is there any periodicity to it? Does it get brighter and fainter, or is it always the same? And then how is it distributed? So, if you're looking at galaxies, you want to see where things are clumped together, where there is no light, where there is lots of light. And so it's kind of amazing that you can actually tell so much about how an object works when it's, maybe billions of light years away from you. You will never go there.
As long as humans have been around, there's no doubt we've looked up at the night sky. And even now with our smartphones and technology, I'm pretty sure we've all looked up at the stars and wondered. Maybe you were sitting on a dock on a summer night. Maybe you were camping far from town. Maybe you walked out your front door and caught a glimpse of some stars, even with all the lights around. Despite that history of looking up, so much of what we know about the stars in space is relatively new.
We only figured out what drives stars less than 100 years ago.
And not having words to describe what astronomers are finding is not surprising.
We look at things, we're like, this is strange. We try to fit it into something that we already know. And then eventually we realize, that doesn't work. Gotta come up with a whole new object or a whole new type of thing to kind of explain. And you have to be, it's actually very creative to come up with a whole new thing.
And convince people
yes,
that you're not crazy.
That it's real. This is actually there.
As Dr. Hamden mentioned earlier, astronomy is in many ways the study of light. Lots of different kinds of light, but still light, because we can't go to most of the places that astronomers study. And for that light gathering, we need telescopes.
People sometimes envision the telescope as the kind of long tube on a tripod that's in your backyard, or they think of a dome somewhere on a mountain that is a big telescope on the ground that's looking up. But both of those are really a very limited set of what all telescopes are. And There are also telescopes that are in the stratosphere, like on balloons. There are telescopes in space. There's even LIGO, the interferometers, which are measuring gravitational waves, which is that's a type of telescope. It's just not looking at light. It's looking at this other signal type. So yeah, the proliferation of types of telescopes in the last 30 years has been really incredible. And there's constellations now where you have multiple telescopes in space. It's cool because constellations and things like that were not possible even 10 years ago.
My dad got me into telescopes and amateur astronomy, helping him lug what we called our big scope out into the Everglades to look at planets, galaxies, and comets like Kohoutek and Halley. And now, decades later, you can still find me out away from city lights with my own telescope, and now cameras, taking photos of the final frontier. When it comes to telescopes, the key is the mirror. Larger mirrors mean more light gathering, which means you can see things further away and more clearly. For very amateur astronomers like me and Dad, the mirrors are often less than a foot across. Plenty big enough for what we want to see, but not for research. For those telescopes that sit on lonely mountain peaks, the mirrors are much larger, with the largest single mirrors being about 8.5 meters or a little more than 27 feet across. That's not something you buy at the local hobby store. For these largest telescope mirrors, you leave Dr. Hamden's office at the Stewart Observatory on the University of Arizona campus and head down the street to the football stadium, specifically under the grandstands on the east side. Yes, as Will Clodfelter, the community outreach coordinator for the Caris Mirror Lab, explains, the mirrors are made under the football stadium on the UA campus.
It's an interesting place to put a facility like this, but it actually makes a lot of sense. You see, football stadiums tend to be large load-bearing structures, and so we knew we were going to have that for our large overhead crane to actually facilitate the movement of our mirrors at the beginning processes. And so by building here, we can enclose the space by only building 3 walls and only 1 load-bearing wall, because the stadium functioned as the 4th wall and that second load-bearing wall.
The rowdy crowds don't cause problems for mirror construction, though testing of the mirrors cannot be conducted during home games due to the vibrations caused by the crowd. So how did the University of Arizona end up with the Mirror Lab?
Ultimately, it was the process of wanting to build larger and larger telescopes. As I had mentioned earlier, we want to have better resolution and better detail, and it's a fundamental physics problem of you need a bigger mirror to have better resolution and better detail. So astronomers always want a bigger telescope. They always want to build something larger than whatever the previous generations is. But oftentimes it's a cathedral building process. It takes a long time to develop telescopes. It takes a long time to build the facilities and get them all operating. But with that being said, there was a physical limitation up until relatively recently with the founding of this facility, because for, I think it was about 4 decades, Palomar was the largest telescope in the world. And it was the largest in the world because there really wasn't a way to build much of anything bigger due to the structural limitations of the glass itself. They had tried to lightweight it a little bit. They actually broke their first mirror in the process of trying to make it. And so it wasn't that astronomers didn't want something bigger, it's that they simply couldn't build something bigger, at least not at the time. And so as technology progressed and as ideas came to fruition, that's when Dr. Roger Angel steps in a little bit and started to experiment with not only spin casting, which drastically reduces the material waste of manufacturing a mirror, but also experimenting with honeycomb mirrors, which we still use today. That eliminates about 85% of the weight of a traditional mirror while still maintaining a lot of structural integrity. And by doing those 2 processes, it's allowed us to expand beyond that threshold that just simply wasn't feasible in the past, and also be able to manufacture them more quickly. They're still on the order of years, but they're not on the order of decades.
To put some context into what Will was saying, the mirror he mentioned as the largest before UA and Dr. Angel got involved was at the Mount Palomar Observatory. It was 5.1 meters across, so smaller than the largest mirrors built at UA, and that mirror weighed 14.5 tons when it was installed in 1949. And before we get any further into this, a quick definition of spin casting, since it's such an integral part of constructing those giant mirrors.
So spin casting is actually pretty straightforward. Anyone who's ever made a cup of coffee or tea in the morning, if they've ever stirred their liquid, they know exactly what spin casting is. When you stir that liquid, you create basically like a funnel shape, right? Or like that whirlpool shape. And that is exactly what we're looking for. It's not exactly perfect. It's not the parabolic curvature exactly that we're looking for, but it removes a tremendous amount of material and gives us a good approximation of that curve. And of course, there's a lot of math that goes into this as to exactly how fast you spin the furnace, because that's dependent upon what the steepness of the curvature of the mirror you're trying to produce is. But the long and short of it is, if you do that math, you can find out exactly what rotation rate to spin the furnace at to get as close as possible to your idealistic curvature, which saves you a tremendous amount of polishing and grinding time, and it also saves you a tremendous amount of material cost because you're not now just carving that out. Traditional telescopes were basically cast like a giant hockey puck, and then you would spend a significant period of time carving a curvature into it. We don't have to do that as much. We already have the curvature. We have to refine it instead.
Again, let's add a little context. So the spinning furnace causes the glass for the mirror to curve, so less glass is needed since you don't have to grind it away. When the mirror for Palomar was built, Will says it started out at about 18 tons, and then had somewhere in the neighborhood of 4 tons of glass ground away to get the right curvature. The UA process doesn't require anywhere near that level of grinding. Oh, and the glass that's used is not the same stuff that makes up our drinkware.
It is E6 borosilicate. It's manufactured by the Ohara Corporation in Japan. They basically make these in a more or less traditional way using clay pots, and they load about a ton's worth of material in. They have their own special recipe and whatnot. They heat it up, mix it properly, cool it back down, and then they break the clay pot apart, and they're left with a cylinder of glass. They take cutting torches and they cut it into irregular chunks, and they inspect each and every single one of those chunks for impurities. Assuming everything's perfect, they ship it to us, and then we can actually put it into our mirror. Now, we use this glass, borosilicate glass specifically, for its thermal expansion properties. Listeners might be familiar with Pyrex. That's a very similar type of glass. It's a borosilicate, or at least old Pyrex was. Now, it is not Pyrex, it's not manufactured by Corning, but why do you use Pyrex? Well, you use it because you can subject it to heat and cold temperatures, and it doesn't break under those stresses, and that's what's a low coefficient of thermal expansion. In astronomy, when we finish manufacturing our mirrors here, they are accurate to a millionth of 1 inch, or about 18 nanometers or so, sometimes better than that even. And so any changes in shape due to temperature variations would mean that that mirror would no longer be accurate. And so by using a glass that has a low coefficient of thermal expansion, we're able to maintain the shape of the mirror night in, night out. And that's incredibly important. Again, another historical parallel there is because our mirrors have that low coefficient of thermal expansion, and because they're hollow, so they have less thermal mass, they are able to be operated much earlier in the night, because there's even one more benefit of them being hollow. We can actually force cool them. And so traditional observatories will take a couple hours after sunset to cool down and get their mirror acclimatized to the surrounding air. And if they didn't do this, it's no different than if you've seen a road on a hot summer day. That shimmering effect, those are convection currents, and that is something that is very detrimental to astronomy. So with our mirrors, because they're hollow, because they don't change shape as much, and because we can force cool them to ambient, they are more productive in general as well, and provide better resolving.
Back to the process of mirror making.
When we're finished with the spinning furnace, we're accurate to approximately 1/4 of an inch or so from our final perfect curvature. It'll be taken to our grinding station after that, and the grinding station gets us to roughly 1/1000th of an inch on both the front and the back side of the mirror. And we do the back side because it provides us a stable and flat surface to polish the front from, and we install load spreaders which mechanically connect our mirrors to our support cells, as well as when they get to the observatory proper, it'll be what mechanically connects them there as well. Once that's been completed, it'll then be taken to the polishing station, and the polishing station is where we do that really refined work to get it to that millionth of an inch of accuracy. Now, how we do that is we do it very, very carefully. So it is not a process of just polish everything and then hope, you actually get effectively what's called the topographical map effectively. And we have a test tower. It does many different tests. There's a lot of different test instruments, but to keep it simple, it provides effectively a topographical map. And that shows you where your high spots are and your low spots are. We take a polishing wheel out to the high spots, and we can apply pressure on it and rub on the surface of the glass. Now, depending on where it's at in the process, that dictates exactly how that is done. We have polishing pads, and we also have a slurry that is used, just again, depending on where it's at in the process. But we find those high spots and we shave them down a little bit. Here's the key part, though. It's a little bit, because we don't want to take Mount Everest and turn it into the Marianas Trench, because there's no way to put glass back on. And so we have to be very conservative and very methodical when it comes to manufacturing these mirrors of we polish a little bit and then we go check our work. Then we bring it back, we get a new topographical map, and we do the same thing over and over and over again as we get more and more refined to better better have a grasp on exactly where we should polish and make sure that we never polish too much on any particular spot.
That polishing and grinding is the longest part of the mirror making process, and it takes a couple of years to get the mirror finished.
You know, in the time it took me to give an example, your fingernails have grown past our specifications, and we're keeping that across the entire surface of a 8.4 meter mirror.
Making huge, precise mirrors is difficult enough. But the Mirror Lab is now making the individual mirrors, which are part of a 7-mirror group that make up the mirror for the Giant Magellan Telescope.
What that means is the outer 6 pieces, the outer 6 mirrors themselves, which are kind of arranged like the petals of a flower, those are what's called an off-axis mirror. And that really hadn't been done on large scale before, because it means that you have 2 axes of curvature. And that's very complicated to manufacture. So the long and short of it is we had to basically reinvent the wheel to figure out exactly how to do that process.
Thanks to Will Clodfelter with the University of Arizona's Caris Mirror Lab for explaining that process. Let's head back across the UA campus to Dr. Hamden's office. In addition to all the other titles she has, she is the Deputy Principal Investigator of ASPERA, a new satellite-based telescope NASA is getting ready to launch.
ASPERA is looking at galaxies that are very close to our galaxy. And, you see these galaxies, and what you really see are the stars in the galaxy, because that's what's putting out all the light. But the galaxy exists in this much more complex environment. And what ASPERA looks at is not the galaxy itself, but it's the stuff around the galaxy, almost like the galaxy's atmosphere. It's a very tenuous gas, mostly hydrogen, that is hard to observe because it's just hydrogen floating out in space. It's not in a star fusing into helium and putting out a ton of light. So the observations that ASPERA will make are the first of its kind to kind of see what this environment of the galaxy actually looks like, how much gas is in its atmosphere, how is it structured? Is it just like a ball of hydrogen around the galaxy? Is it more structured like filaments, or is there nothing there?
Having ASPERA look at the environment around the galaxy, which helped to turn it into what we see today, could answer a lot of questions.
We are looking at star-forming galaxies, which are similar to our star-forming galaxy. It will help us to understand how our galaxy got here and how our star forms. I think in a bigger sense, the point of research like this is to discover things about the universe that we think are interesting, but that we don't know what's going to matter in 100 years or 10 years or 50 years. We will learn about galaxies and a little bit about how they work, and maybe we'll find out that our paradigm of galaxies is wrong, and we need to come up with a new understanding of the universe.
A UA-built mirror that was put in a telescope relatively recently is also making big discoveries.
The Rubin Observatory down in South America, that we built the primary mirror and the tertiary mirror, so the first surface and the third surface, in a single piece of glass. And that design allows it to have an extremely large field of view. So this telescope is scanning the sky. I think it takes a complete picture of the night sky every 3 days, and it returns over and over again to the same fields, because we're looking for things changing, like, oh, a supernova went off in this galaxy, this star suddenly got brighter, here's something moving in the foreground. So it is a discovery machine for things changing. So in the first a couple of days that they were operating, I think it found 3,000 asteroids. And it's going to find 3 million asteroids, all in our solar system, and all stuff that we should know where it is and what they're doing. But, when we talked earlier about we're just measuring light, previously we had been measuring things that were relatively static, or that they change, but you don't maybe know how quickly they're changing, or you happen to catch something that is bright and then it's dim, but you don't have the kind of continuous time coverage to say anything about it. And now with some of these new observatories, like, you're checking on objects all the time. So now there's a time dimension, not just, how much light is hitting your telescope from a particular object, but how is that changing every hour, every day, every month.
So who knows what we'll see when we look up at all those little lights in the night sky. And that's it for this episode of More to Know. Make sure to like and subscribe so you never miss an episode. Thanks to Will Clodfelter and Dr. Erica Hamden for their time. To learn more about the stars in space in a way non-astronomers can understand, make sure to follow Dr. Hamden on social media and check out her book, Weird Universe. And thanks to friend of the show Katya Mendoza for her help on this episode. Our producer is TJ Spiker, and our music is by Enter the Haggis. I'm Christopher Conover. Thanks for taking the time to find out there's always more to know.